Hello, everybody. There are some other trig functions that you might not know about. This one is cotangent, this one is secant, and this one is cosecant. We're going to touch on all of these functions a couple of times throughout the semester, so this is just the initial introduction to them. Let's start by filling in this blank with what we know already, though. Sketch a little circle, unit circle, which means that it is a circle with radius 1. What we know already is that for an angle theta, there will be a particular point on the perimeter of the unit circle with xy coordinates, and the x-coordinate is just cosine of the angle, and the y-coordinate is the sine of the angle. So these other functions we're going to learn also have geometric interpretations. In fact, these aren't the only ones. If you extend this line that goes to the point on the unit circle all the way until the x-coordinate lines up with the edge of the circle, so it's got an x-coordinate of 1. This total height is the tangent of theta. But there are other geometric interpretations for tangent theta as well, and for all of these. Those are not going to be so important for us for now. I just wanted to show you what they were. For now, let's dive into how they actually defined. So tangent theta, you know, is sine over cosine. Remember, if sine is telling you, here, let me get a different pen color. Okay, so if sine is telling you the y-coordinate and cosine is telling you the x-coordinate, you can also think about this as being y over x, and you should notice that that's the same thing as the slope of this line here. So you can think about tangent as telling you slope of the line that takes you from the center of the circle to the point at an angle theta. Okay, so cotangent is defined as the reciprocal of tangent. So it's 1 divided by tangent. That's what reciprocal means. It means that you've reciprocated it. It's flipped upside down. If we were going to do, so if I was going to fill in the definition of tangent here, I'd have 1 divided by sine over cosine. And so if I was going to simplify that, I could flip it and multiply to give me cosine over sine. So either one of these would be a great way to rewrite cotangent, and sometimes one is more useful and sometimes the other is more useful. So both of these are going to be really important to know. Secant and cosecant. Okay, so secant is 1 over cosine theta. Cosecant is 1 over sine theta. If you think you're likely to forget how these are pronounced, you can go ahead and add a little pronunciation guide. So we'll do this as cotangent. This is going to be secant, and this one is cosecant. Okay, so you are definitely responsible for knowing these basic definitions. People want to know, why do these other trig functions exist? Why are they helpful? There's a lot of answers to that question. So some of the functions, like secant, have very important applications, like the Mercator projection, which is a projection of like a spherical surface onto a two-dimensional surface, which is what all our maps are, uses the secant function in a really important way. There are other functions, there are other applications as well. I would say for your immediate future, the reason you could do all the trig you need without all these functions. Instead of secant, we could always just write 1 over cosine, and all your math would work out just fine. So these are mostly there for convenience and for notation. It will help clean up equations and make them look more approachable, look less messy. Because if you're always writing equations and you're constantly seeing 1 over cosine, it might help to just name 1 over cosine with a different name, and then it'll look less messy. So I think that's a good way of thinking about why we have these. Again, to be super clear, you don't need to know the geometric interpretations of secant and tangent and cosecant and all that. They're not nearly as important as the geometric interpretation of sine and cosine, which you use literally all the time, like every time you look at them almost. Okay, last bit is conceptual, just about inverse trig functions. So if I calculate cosine of 12.3, the 12.3 is an angle, and cosine 12.3 represents an x-coordinate. That's not new. You knew that before. What about this? So this is inverse cosine. Remember that inverse cosines, inverse functions in general, will undo the action of the original function. And a way of thinking about that is they will take whatever the output was and turn it back into the input. So if cosine turns an angle into an x-coordinate, inverse cosine should turn an x-coordinate back into an angle. So point 3 would represent an x-coordinate, and inverse cosine point 3 would represent the angle, or rather an angle, that has that x-coordinate. There is more complexity to these, having to do with domain restrictions, and we'll talk about that at a different time. Right now, I just wanted that conceptual piece in place so that you're not staring at this thinking, what in the world is that even talking about? Okay, come back to the next video, and we'll kind of wrap up some big takeaways from the problem set.